Welcome to part 7 of vector spaces. So we're working with P sub n, the set of all polynomials of degree n or less with coefficients defined to be complex numbers. So here we want to think of P sub n to be what we were denoting as V, okay? And so we're considering what is the equality on this set V and what is going to be vector addition. Notice that here the intention of using the word vector is because P sub n, polynomials of degree n, is a vector space. So when we say that U is in V, okay, we want to think of U in this case as this form, and then we say little v is a member of this vector space, then here is that little v. This would be the little v. So because of the definition of this set being polynomials, then here U is an expression that looks like U is a sub k x to the k, where k runs from 0 to n, and also v is an expression that looks like b sub j x to the j, where j takes values 0 through n, right? So u has an expression as a polynomial with degree n, v is a polynomial with degree n, and the question is, if we say u plus v, what do we mean? Well, nothing other than adding polynomials, right? So when we add two polynomials, we would say that those polynomials are added and you collect all things that have the same exponent, right? So we know that, you notice that a0 multiplies x0, b0 also multiplies a power x0, which is 1. So those two things are grouped together, and then the terms multiplying x to the 1 are a1 and b1, so they are actually collected together, and if you factor x as a common factor, this expression reads a quantity a1 plus b1 multiplying x, similar for powers of x2 and for powers of x3, right? So you start collecting all those coefficients of these expressions, and this is what you end up with, which is on its own right a polynomial of degree n, right? So this will be considered the definition of vector addition, and scalar multiplication. If we are multiplying scalar alpha times an arbitrary member of P sub n, then because of properties of complex numbers, or because of properties of the scalars that you may be using, right? This scalar multiplication is nothing other than distributivity across addition. So you end up with something that looks like this, where this is now the new coefficient. Alpha a0 is the coefficient of the power x to the 0. Alpha a1 is the coefficient of the power x to the 1. Alpha a2 is the coefficient of the power x to the 2, and so on. So this is indeed another polynomial, and this polynomial has different coefficients than a0, a1, and so on, but this is still a polynomial of degree n, okay? So what comes next to argue is, given these definitions of equality, vector addition, scalar multiplication, is it true that P sub n is a vector space? Well, the answer is yes. P sub n is another example of a vector space, and what you should do right now is pause this video. What you should do right now is pause this video and do an examination property by property. Go through all those 10 properties and check for closure under addition, closure under scalar multiplication, every single one of those properties. Confirm that they are all true with elements of P sub n and with this definition of addition and scalar multiplication. Another example of a vector space is a set of functions defined here from any domain that is mapped onto the complex plane. these functions have the definition of equality, that any two functions are considered equal if they are equal at any point in the domain. The addition is defined as f plus g at x, f of x plus g of x, and the scalar multiplication defined as alpha f evaluated at x is no other than f of x multiplied by alpha on the left side. So with those definitions, we find that this is an example of a vector space. And now we arrive at this other example, or counterexample. And so here you may be wondering, why is there a 1? Well, this set is simply you could think of this as a subset of C sub 2, or you could think of it as C sub 2. But what is different here is the definition of vector addition. And this is not the usual. Remember, we were using up until now this word, the usual vector addition. This is an operation that, as odd as it may seem, this is the definition of addition. When you're exploring operations on sets, you may explore or define your own definition of an operation. And so is the case here. So for example, if you were going to consider, I don't know, you could consider 1 and 2, this being an element of C, as the way in which C is defined over there. And you may consider, for example, 1 plus I and 2I. Okay, this is also another member of C. So according to this definition, you may say 1 plus 2 plus 1 plus I, 2I. And here, when you say equal, you can use this is equal in the definition of addition according to this definition right here. And that definition says you take this wasn't a plus here, this is supposed to be a comma. So you take this vector u and take this vector v, okay, and you're gonna add them, and you're gonna end up with another member of C2, such that the first entry here is computed by adding the first entries of both of these vectors and adding 1 to it. So we would need to involve here 1 and 1 plus this is supposed to be I, right? So this would be 1 plus 1 plus I, and then we would need to add the number 1, because that is what this definition is telling us. Similarly, for the second entries, in which we would have 2 plus 2I plus 1, because that's what this definition says. So according to this definition of this operation, here we would have 3 plus I on the first entry, and then we would have 3 plus 2I on the second entry. And so these are not what would come out by using the usual definition of vector addition, but this comes out by using this specific definition here. And the scalar multiplication is also defined a little strangely, right? It says that if you multiply alpha times u, where, see here, this is, say, u1, u2, then that this is alpha u1 plus alpha minus 1, that this would be the first entry, and the second entry would be alpha u2 plus alpha minus 1, right? So this is rather nothing at all like the usual definition of scalar multiplication. And so what is the challenge here is that you need to pause the video right now, and you need to go and review that every single one of those 10 properties. You need to check, determine whether or not every single one of those 10 properties that define a vector space hold true if these are the definitions of vector addition and scalar multiplication. And lastly, but not least, there is a number of theorems here that are also reinforcing some of the properties of vector spaces. If the zero vector, which is required for the vector spaces, for the set to be called a vector space, it exists and is unique. Additive inverse, something denoted with a negative here in front of it, is also unique. In a vector space, the scalar multiplication 0, the scalar 0, this 0 here is the 0 in the complex plane, right? So this here is 0 plus I times 0, or 0 plus 0i. That's what is considered 0 as a scalar. If you multiply that scalar in scalar multiplication by a member of V, this being an arbitrary member, then you get the 0 in V, this being the 0 vector, right? That is defined in one of the properties for a vector space. And if you multiply an arbitrary scalar times a 0 vector, you would get the 0 vector. That's the next theorem. The inverse under the addition, also called the additive inverse, is equal to the scalar multiplication -1 times u for an arbitrary vector u. Okay, and in a scenario in which if you have an equality, the definition of equality is determined by the specific vector space. If that equality is something, have a scalar multiplication equal to the zero vector, the member of the vector space called the 0 vector, if you have that equality, is because either the scalar alpha is 0 or the u in that scalar multiplication is the 0 vector.